Hi there, welcome to the presentation of our research work on data-aware global explainability of graph neural networks. Let's get started. Graph neural networks are powerful, but these models are not yet fully trusted because of their black box nature, and users cannot verify if the model is truly reliable. As a result, many explainability techniques have been developed. A GNN explainer aims to answer the question, which part of the input leads the model to make such a prediction by identifying a critical substructure from the input data. Existing methods can be categorized into two groups. Local explainability stands for instance-level methods, which explain a target prediction on a specific instance. The other group is global explainability, which corresponds to model-level methods. Global explainers provide a higher level interpretation of the model's behavior, and they also provide easy generalization to an inductive setting, which is the nature of many GNN applications. In this work, we focus on model-level explanation to understand GNNs from a global view. An open issue in explaining black box models is the absence of a unified evaluation scheme for measuring explainability. Without coding knowledge, the key challenge lies in quantifying the quality of an explanation. To tackle this problem, we analyzed the interrelation between GNNs and their training data. We found that in some situations, output of existing methods cannot serve as good model-level explanations. We will show them using the MoTeX dataset, which consists of molecular structure classified by their mutagenic effect. In these molecular graphs, nodes represent atoms and edges represent chemical bonds. Case 1. The generated explanation is not recognized by the GNN. Shown in the red box is a 6-carbon ring followed by an existing method as an explanation for the mutagenic class. However, its prediction score from the GNN for the underlying label is less than 0.01, which means the model does not recognize this structure as mutagenic. Case 2. The generated explanation does not exist in the data. A typical example is the explanation generated by XGNN, which is an existing model-level explainer. One of its outputs is shown in the red box. The structure violates the chemical rules. Take the oxygen atom as an example. The maximum absolute value of their valency is 2. However, their degrees in the structure are 4 and 6 respectively. The same problem also happens with other atoms in this structure, so the rationality of this explanation structure is doubtful. Case 3. The generated explanation does not discriminate among classes. For instance, a carbon ring attached with an NO2 structure found by GNN explainer as an explanation for mutagenic class, it receives a very high GNN score and exists in 91% of the graphs in that class. The issue is that this structure also presents in 84% of the instances in a non-mutagenic class. The explainer is then trapped in a situation where graphs containing an explanation for some class are actually predicted as another class by the GNN. So essentially, the first case demonstrates that existing explainers may fall short from the model's perspective, and the other two show that current techniques may fail from the data's perspective. Thus, in this work, aiming to achieve the best of both worlds, we propose a data-aware global explainer to tackle the discussed drawbacks. Moving to the methodology part. Global explainer aims to find a set of substructures that best explain the model, and we consider the candidate space of subgraphs mined from the training data of the GNN. For the sake of guiding the optimization, we first conclude the properties that global explanations should preserve based on our observation, then further design metrics to evaluate the candidate. Corresponding to case 1, we have the first property of high-quality explanation candidates. That is, it should be highly recognized by the GNN. We then define the faithfulness of a candidate to be its prediction score given by the GNN, which is just a direct measurement of model recognition level. For the second property, we believe a high-quality explanation should be compliant with the data distribution and define the support of a candidate to be a set of instances from the target class that contains the candidate's subgraph. In other words, support represents right class presence of the candidates. Naturally, the size of the support sets can be directly employed as the metric for measuring property 2. Lastly, we have the third property of a high-quality explanation. It should be discriminative among classes. The corresponding metric defined is called denial. It is the set of instances from the other classes that contains the candidate's subgraph. Analog to support, denial represents wrong class presence of a candidate subgraph, and the size of the denial set is then considered a matrix for measuring property 3. With the help of metrics on individual candidates, we now define how to qualify the global explanation set. Primarily, we consider the overall fidelity of explanation set as the average faithfulness of each single candidate in the set. Secondly, we favor a set with higher overall support, so we consider the union of support set of individual candidates. Different from support, we care more about lower denial. Thus, we design the corresponding object to minimize the average denial ratio out of all explanations in the candidate set. Finally, we seek for an explanation set of a smaller size for ease of human understanding. All these components are normalized by dividing them using the corresponding upper bound so that their value will be between 0 and 1 to match the range of GNN score. We now propose our integrated learning objective as the weighted sum of the above introduced components. The non-negative weight parameters, lambda 1 to lambda 3, actually represent the relative importance of the component. We have proved that the objective function is weakly submodular, such that maximizing it is NP-hard. Then we can go ahead to apply the random greedy algorithm to find a near optimal solution. This is how random greedy works. In each iteration, the algorithm first constructs a candidate pool M of size K, where every candidate retains a positive marginal gain given the current explanation set. In a case where the number of candidates with positive marginal gain is less than K, dummy variables with a virtual marginal gain at 0 are supplied to make sure the pool is of size K. The algorithm then iteratively picks candidates with non-negative marginal gain with a probability 1. As a result, we can ensure the objective function increases in each iteration. The algorithm is actually quite efficient as it has the same cost as the standard deterministic greedy algorithm. The current best bound of random greedy algorithm on optimizing weakly submodular function in our problem is shown here, where C is the candidate space, namely the set of subgraphs mined from the training data. The guarantee is rather pathetic because the candidate space is usually very large, while our objective function has a particular structure with one component as weakly submodular and all the others as submodular. Based on this, we derive an improved bound for applying random greedy in our problem, and we welcome you to check out the proof in our paper or technical report for this theorem. We hope you find it useful because it is universal for a set function like this, but not just restricted in our problem. Coming to the experiment part, because the algorithm is randomized, we simply run it for 1,000 times and use majority voting to get a final output. For evaluation, from the model's perspective, we use the average GNN score as a metric. In fact, prediction score of the target class is used as an evaluation metric in many existing model-level methods. As for the data perspective, we define a metric called self-support, which equals the size of a support set over the total size of a support and denial set. This metric will help us understand if the explanation is discriminated among classes. For candidate generation, we use GSPAN algorithm to mine substructures from the training data because it is used by one of the competitors, but essentially any graph mining tool can be plugged in to help. We compare our method to 2 existing model-level explainers on 1 synthetic dataset and 2 real-life datasets. Furthermore, we trained 2 GNNs on its acyclic and mutex dataset to see if there is any difference in their decision-making mechanisms. Overall speaking, that explainer outperforms the baselines and generates explanations with high model recognition and outstanding data awareness. On the acyclic and mutex dataset, all of the final output of our method have a prediction score of 1, and it is greater than 0.9 on high school dataset as well. The data awareness level is affected by the original graph data distribution, but that explainer has at least 0.8 self-support on the 3 datasets, and mostly it is 1.0. Regarding running time, DAG explainer outperforms the competitor if candidate generation is not counted. Note that candidate generation for DAG explainer on a dataset can be used to explain any GNN trained on the dataset. This is extremely helpful in a situation where different GNNs need to be compared on the same dataset. For instance, if one intends to facilitate neural architecture search for GNNs with explainability, once the candidates are prepared, DAG explainer can fully enjoy its high efficiency in repeating explaining searched GNN architectures. For the qualitative analysis, we visualize the result on its acyclic dataset. The dataset has two classes. One is cyclic class, which contains grids, cycles, and ladders. The other one is acyclic class, consists of stars, trees, and paths. DAG explainer finds a ladder structure for gene model and a ring structure for GCN model as cyclic explanation. Meanwhile, the method outputs a star-like structure as acyclic explanation for the two GNNs, which concisely summarize the generation rule of the synthetic datasets. Here is the result on MUTEC dataset. It is a dataset with molecular structure of chemical compounds. We used this dataset as examples in the introduction. DAG explainer outputs explanations with perfect data awareness and GNN scores all equal to 1. Notice that explanation by DAG explainer for the gene model are very similar to some for the GCN model. We suppose such results show the similarity and difference between decision-making mechanism of these two GNNs, which can help human users understand both models better. Meanwhile, the output of XGN are shown in shaded background. They are all out of distribution, meaning they do not exist in the input data. The rationality of this explanation are doubtful. The other competitor, Glocal Explainer, also finds high-score explanations for both GNNs, but they are not discriminated between classes. MUTEC dataset is an obvious example to show that existing methods are not data-aware. Finally, we have the high school dataset, which is a social network dataset, where each graph is a face-to-face contact network between high school students. There are two kinds of epidemics spreading in the social network, a high-risk one and an ordinary one. In the visualization, infected students are represented by red nodes, while non-infected are represented by green nodes. Safe contact is shown using green edges, while risky contact is represented by the red edge. We further thicken a risky contact if infection happened during this contact, which is then considered a part of the epidemic propagation. For the ordinary epidemic class, DAG explainer captured no infections as we expected. None of the outputs contain any propagation path. Moreover, 2 out of 4 explanations contain red edges that are not thickened, which indicates that the epidemic did not successfully spread even when risky contact happened. For the high-risk epidemic class, we observe evidence patterns for propagation in DAG explainer's output. Every risky contact commits to an infection. The observation precisely aligns with the ground truth that high-risk epidemic is more infectious and dangerous. So it is demonstrated that DAG explainer produce meaningful explanation that verify the trustworthiness of a GNN. To understand if global explainers can really help human users understand graph neural networks in practice, we also designed a user study with 45 postgraduate students working on an online survey. Specifically, we asked the user to guess the GNN's prediction based on the explanation provided by different explainers. Here's the result. Overall speaking, DAG explainer constantly outperforms the competitors on all the 3 datasets. On the acyclic and high school datasets, users are able to correctly predict the GNN's decision on more than 85% instances based on explanation by our method. In conclusion, we propose in this paper a model-level explanation technique. We observe 3 properties of high-quality explanations and design metrics to quantify the degree of an explanation retaining the 3 properties. And the objective function is designed to find candidates that best explain the model. We prove that optimizing the object is NP-hard and adopt a randomized greedy algorithm to find a near-optimal solution with an improved theoretical guarantee. Experiments show that our methods output meaningful and trustworthy explanation with decent quantitative result. Thank you for listening.